All right, time for a discussion of some latter topics from Chapter 4. We have done enough electron dot structures to get a few pieces of this described, but now we need to go beyond that to figure out how there's things that we call resonance structures, because we have to have multiple bonds that might occur in more than one fashion to make sense of the compound. So, in order for us to have a conversation about resonance, it would help for us to have a revisit the drawing of the electron dot structure for ozone, which is O3, and we'll follow through the steps that we've been using to create Lewis structures and see what we get. So O3 is ozone. Step 1, you're going to count up the valence electrons, and there would be 3 oxygens. 3 times 6 is 18. And you skeletally connect them with bonds, so 3 oxygens, 3 bonds. That means you've used up 4 electrons. And so I'll make a note of that here. Minus 4 electrons in bonds. And that gives us 14 more that need to be accounted for. So the next step is to put the lone pairs in on the peripheral atoms. And so if you're not lost in your counting, there's 2, 4, 6 on each of the oxygens. So 12 electrons are in lone pairs on each oxygen. That means 2 electrons remain to be accounted for in our correct Lewis structure. And so the last step is, or the next step then, is to put that extra pair of electrons that is necessary for a complete structure on the central atom. Then if we've looked at the whole structure and tried to decide if it's finished, we're looking for octets. And this central oxygen does not have an octet, so you have to reassign an electron from one of these side or peripheral atoms to the central atom in a multiple bond. And in this case, the diagram is drawn so that we've removed the electrons from the left oxygen atom. All right, so we removed a lone pair from the left one and ended up with a double bond on the left side. But you could have equivalently removed the lone pair from the right side oxygen without it being any different, because those oxygens have nothing unique about their other connections. So what we have to do is decide which is correct, and the answer is both. And that's what we call resonance. Resonance suggests that both of those possible structures with the double bond on the left or the double bond on the right are equally appropriate. A resonance structure is one of 2 or more Lewis structures for a particular compound that cannot be represented accurately by only one structure. So ozone is represented with these 3 red spheres that are kind of squished together on this molecular model on the left. And they're all represented as equivalent, but that's a little tricky to say for that. It actually looks like a cold bubbling liquid in that flask in the bottom left. And if you look at electron density, there's electron density excess on this middle diagram. There's this electron density is what the negative charge is, the pinkish region on these diagrams. And so each of the oxygens has a little end oxygens has a little extra negative character compared to the middle, but not one more than the other. And so the electron, the diagrams we drew on the previous slide tell us that you could either have either of the end oxygens could be drawn with the double bond equivalently, and so we put an arrow in between to represent the idea that they're both equivalent. Neither structure alone accounts for the bonds being of equal length, and the single bond should be longer than a double, so both structures are accounted for, and the arrow in between tells us that these are resonance structures. So double-headed arrows in these diagrams represent the notion that these are resonance hybrids. The 2 together combined give you the full picture. In other words, you kind of have to imagine the electrons, the second bond, being half the time on one side, half on the other. So it's a hybrid of the 2 that actually occurs. So when we're looking at resonance structures, there's one famous example of a compound that has resonance structures. This would be known as benzene. And benzene has 6 carbons and 6 hydrogens. If you put all the carbons in on the corners, carbon having 4 bonds means that each hydrogen or each carbon has a hydrogen attached. And the structure of benzene can be thought of as a hexagon a hexagonal connection between 6 carbons with alternating double bonds. But neither one of these positions, these set of bonds in the first diagram or the second diagram is complete. Neither is correct by itself. And so the arrow tells us that these are resonance structures, so that half the time you can consider the double bonds to be in one position or the other, but neither is correct. Neither is correct by itself, and so it's resonance structures. The way you get around that is by drawing something else that's not double bonds at all, and that happens to be what I commonly use in my other course. So benzene is famously an example of a compound that has resonance structures. Its structure was deduced by a fellow named Friedrich August Kekulé, a German, in the 1800s, and he got immortalized, if you will, or commemorated on a stamp in the former East Germany back in 1979. And there's his structure that was describing the structure of benzene. Interesting trivia piece for you. All right, so if we want to make sense of resonance structures, we need to see some more examples. And they occur for compounds that have multiple bonds, such as the carbonate ion. And we have to think about how the resonance structures contribute to the overall picture of the stability and bond lengths and strengths for a particular compound. So drawing a Lewis structure for the carbonate ion, we have a handy-dandy one ready for us here. So the carbonate ion has 3 oxygens. One of them has a double bond. 2 are singly bound with more lone pairs than the one with the double bond. So you can have your double bond on the lower oxygen, the left oxygen, or the right oxygen. And the 2 that have single bonds have negative charges associated with them because the carbonate ion, in fact, has a -2 charge. The minus charge is localized on the atoms represented with a single bond in these diagrams. The arrows in between the 3 structures tell us that all 3 of these structures, all 3 of these representations of the carbonate ion are correct in combination as resonance structures. Remember that the resonance explains how these things occur. In other words, all 3 bonds between carbon and oxygen, or all 3 carbon and oxygen connections, are equivalent. The double bond is not one place more than the others. And sometimes we're going to write these things with a charge around the entire collection of the ion, atoms in the ion, instead of trying to localize charges on individual atoms for that reason. So all the CO bonds are equivalent in carbonate because of resonance. All right, now let's do one more for the compound we know, the polyatomic ion known as nitrate. And we have an initial drawing here, and we have 6 of 24 valence electrons assigned by making single bonds, and the structure on the right would indeed have 24 valence electrons. That's what you expect because nitrogen has 5 electrons, and 3 of oxygen is 3 times 6, which is 3 times 6 is 18, and the negative charge means you have to add 1 more for a total of 24 electrons. Well, that seems appropriate, doesn't it? But what's wrong with that structure? Nitrogen doesn't have an octet. Needs an octet. So the structure is not complete yet. And in order to do that, you have to reassign some electrons from one of the peripheral atoms to the central atom in a multiple bond. Well, which one do you want to assign? Well, it could be the top atom, it could be the left atom, it could be the right atom. So it's, again, resonance structures that contribute or explain the actual molecular shape and structure of nitrate, where all of the NO bonds are equivalent because no one diagram is correct. It's a hybrid or combination of all 3. And notice in this case, the charge is shown outside the brackets, representing the notion that the entire molecular ion shares that charge. All right, are you ready to try one other conversation? One more with this funny compound called anisole. You don't have to know what it is, but let's draw it out and realize what's missing. And in order for this structure to make sense, carbon's black, right? And this oxygen is connected to a carbon, which is connected to apparently 3 hydrogens. Now, and I didn't finish putting them all in yet, so there's going to be some more hydrogens here. And that hexagon with 6 carbons is going to be reminiscent of the benzene that I showed you moments ago. And so in that structure, carbon doesn't have enough bonds. And so in order for that to be correct, carbon is going to have extra bonds between the carbons in the ring. And so one way you can do it is the carbons in the double bonds could go that way, or the resonance structure is to alternate the double bonds in a different orientation. Again, neither structure alone is correct, but if you put all three in combination, or both in combination, there's two here, then you have a more complete representation for the structure. And so instead of having the multiple bonds the way I showed them on the left, that was supposed to be double. Okay, make that really double. And you put them in the alternate positions, and you have two resonance structures for anisole. So it gives you an idea how these things can be done and how they contribute to an overall structure. Another way of getting around trying these resonance structures will be to show a hexagon like this and a circle in between with oxygen and then CH3. That is used by some people to represent the fact that neither one of those structures individually is correct, representing actual double bonds. Okay, I hope that helps you. Good luck with your homework. Let me know if you have other questions. The next recording will be the next section of the chapter.